Okay, so nobody's going to introduce me. I'll start. First, okay, I have to turn this on. First, a legal notice. Are there any minors in the audience? No, good. It's really good. If by any chance you get offended by any culture and historical references I'm going to use during the presentation because of your gender, sexual preferences, education, race, age, or basically anything, please feel free to feel offended. Who am I? I'm Dominik Pantůček. I usually talk about some cryptography stuff and security. I'm running a consultancy company, Trustica. We cover what I just said, the security and some sort of weird development. In our current products, we focus on using advanced cryptography using elliptical curves for providing some security solutions. And we also developed a ransomware detection and mitigation tool lately. But sometimes we need to get down and dirty in day-to-day operations. And that's why this talk. It's going to be a double feature today, because following my talk, you're going to see Tomáš Kukrál's talk about monitoring the Ceph cluster's health. So stay after I finish. It's going to be interesting. Also, as with any other double feature, hopefully it will be fun and not only in the back row. So let's get down to it. Why? Why daily operations? As I said, we are mostly consultancy and security company, so we don't need to run many big services. But what we need, we basically need to maintain some infrastructure and be able to provision quickly new services, mainly for testing. So it is for running our infrastructure, testing virtual infrastructure, and basically isolating our projects from each other. What do we need? So we need convenient deployment of virtual machines. Nowadays, you would say private infrastructure as a service cloud. That's the catchy name you need, cloud. Okay, why cloud? As I said, it's convenient. That's the main reason. Why private cloud? Turns out that, and actually it's been the topic of my thesis, that you can negotiate basically everything with cloud providers, provided you have the budget for it and you are big enough to actually make them talk to you. So the negotiations are really tough, and so we chose to run a private cloud. Then the last question, why Ceph? That's rather simple. Everything else failed miserably, really. So, what is Ceph? Ceph is a distributed, highly scalable, open source object storage. Now we should pause for a while. What does it mean, object storage? Well, it's a system for storing objects. That's just it. And by objects, I mean virtually anything. We'll get onto that later. But that's not enough. Imagine you can just store the objects. What would you use that for? Okay, you can store some HTML files, some images. You can run some content delivery network on top of that. But that's not what we wanted. That's not usually what you want. So on top of those objects, you can actually build some really interesting stuff, like block storage. Now, that's handy. It's like a scalable hard drive with something clever behind. Or you can use it for creating a scalable file system, where the size really doesn't matter, because you can get as much as you can actually put into it. And also, as I said, cloud. Everyone is talking about cloud these days. You can use it for other applications. By other applications, I mean something like Amazon S3, the simple storage service, or the content delivery network built on top of that. So that's what you can actually build yourself using Ceph and other components. Well, Ceph is better than sex with animals, and I can assure that, because if you ever tried sheepdog, That's another object storage system. It's rather clunky, and there's not much. There hasn't been much development lately. It's sort of basically done, but with Ceph we got new features with each stable release, and they're quite handy. The thing is that Ceph is structured in a way that allows not only the current version and current features to scale horizontally and vertically, but also allows for adding new components fairly easy. That's because the architecture itself splits the whole cluster into, I would say, something like subclusters. And by subclusters, I mean functional parts of the main cluster. It's still a single big storage cluster. There are daemons which represent different functionalities of these modules, of these subclusters. The first of them is OSD, Object Storage Device. Now the terminology is a bit clunky because OSD is actually the physical device on which you will store the data, like a hard drive or, well, another hard drive, basically these days. You're not going to store it on tapes. That would be really slow. But also, OSD is used as the name for the daemon that is used to manage the actual physical device. The proper name is, of course, Ceph OSD, but who cares nowadays? Another daemon is the monitor daemon. And if any of you, by the way, could you raise your hands if you ever got your hands on high available clusters? Any kind of high available clusters? Cool. Now you'll be at home because the monitors, all the monitors of the Ceph cluster comprise basically a highly available cluster for managing the whole system. There's all the things you know you need to get some quorum, voting majority and things like that. And that's what holds the Ceph cluster together. Also, with the latest releases, we've got the metadata server, MDS. I said you can store objects. It's not the whole truth. You can actually store objects and add any metadata to it. But you can have millions of objects, you can have various numbers of metadata associated to it, some extended attributes or whatever you want. So it's rather slow to actually retrieve this metadata information because you need always to pick just one thing like, say, permissions or some hash or owner or whatever. So that's where the metadata server comes in. If we wrap it all around, we can look at the cluster in a completely different way, from the point of view of physically deployed nodes. And the good thing about Ceph is you can actually have combined nodes. I'll just talk about their types, and then I'll get back to this feature. First, you can have nodes with OSDs. That's the most of your nodes. You might have a few thousands of hard drives. You don't want thousands of computers running them. You want to stack as much as you can into a single chassis. But you need to keep it separate in order to provide some redundancy. Then you got the monitor servers, monitor nodes. Those are the nodes that, as I mentioned, manage the whole cluster and keep it together. You do not need many of those, but keep in mind, and once again, we'll get onto that later on, it's good, you don't need to, but it's good to have an odd number of them. And of course, the MDS, if you want to run some advanced features of the cluster. Then, important thing, client nodes. Although not actually part of the cluster, but they may be, as I said, you can have multiple functional nodes on single physical node. Those are the nodes where you run your applications that actually use the data, store and retrieve. And it's important when you are planning Ceph deployment to actually think about how you will access the data in the cluster and how do you want to deploy your Ceph client nodes. where you will run those applications. Also, there's one, I call it abstract node. It's the admin node. You'll find that if you read the documentation, fairly often mentioned. It's not a node per se, but it's handy to have one. It's a node from which you can quickly deploy new cluster nodes. You can do some maintenance, anything you want. It can be your laptop, or it can be a virtual machine on your VM solution. It can be one of those nodes, but that depends on your specific scenario. So just bear in mind, it's handy to have one. Let's sort of disassemble it even more. We've got, as I mentioned, the Ceph OSD, the physical device and accompanying daemon that will manage the data on the OSD. It's, as I said, a disk, or it can be just a part of the disk. Imagine you are running a server node where you want to have some, say, RAID 1 array for booting the operating system. It can consist of, say, 8 disks in RAID 1. Why not? But you don't need much space, just a few gigabytes of data. And then the rest of all those disks, you may use those partitions as OSDs for Ceph, so you don't waste anything. That's useful. Also, it's, as I said, the name for the Ceph OSD daemon. And once again, as I said, you can have multiple OSDs in one physical node. All of this managed by the monitors. So what is a Ceph monitor? Ceph monitor is something that contains the information about the cluster, the runtime information. And in Ceph, by information about cluster, we mean cluster map. It's actually not a single map. It is a set of 5 maps. First, the monitor map. The monitors itself, although they manage the cluster, they have to know where other monitors are. And if you are a client, you are connecting to the cluster, you need to know only one monitor. And if you connect to it, it will give you addresses of all other monitors. Also, if you are an OSD node, you want to add yourself to the cluster after authentication. Once again, you contact monitor node, at least one, you get the monitor map, and you can redundantly connect to the cluster management. The monitor map contains epoch number. That's basically the revision number of the map, beginning with number 1 when you first deploy your cluster. The last modify time, and then address and a port for each running monitor. That's it. Then you've got the OSD map. Once again, we've got the sort of revision. That means how many times the set of available OSDs changed from the deployment of the cluster. Last modify time, and then the interesting thing, list of pools. Those are pools of those OSDs. Because when you are actually working with some big data sets, you have no time for trying to find out where to store data on which OSD. That's what Ceph is here for. And you also do not want to use a single cluster for a single purpose. But you can specify multiple pools of OSD and say, hey, let's use these 20 disks for this task and these 100 disks for another task. And Ceph will happily do that for you. So the list of pools, and this is the place where you have defined the replica sizes, which means how many copies of data you want in each pool. Like the default is 3 copies, but it's up to your specific needs, what you'll configure there. Also, it contains the placement group numbers, which is something which I'll get to later on. And it contains the list of all OSDs ever seen with their status, either up or down. We go no deeper here at OSD map. But where we go deeper is the placement group map. What is a placement group? Imagine you have, say, 10 disks. and you have millions and millions of objects, and you want to distribute them uniformly. It's not that hard task, but if the sizes of objects are different, it may become hard. But the problem here is there are really many combinations on which sets of these 10 disks you can store the data. For 10 disks, I think you can quickly do the math. 10 disks, 3 replicas, that's 720 combinations. So placement group is exactly this each combination. And by specifying placement group map, you have virtually pre-calculated everything you need for storing the data. You only need to decide in which placement group you want to store your object, which does also the Ceph itself, and then it can quickly access those OSDs and store the data there. Very, very handy. The important thing here is placement group map is closely tied to the OSD map, because you always have the revision of placement group map tied to the specific revision of OSD map. If you remove some OSDs, add some more, everything needs to get recalculated, which is sort of handled behind the bars, but you have to think of that when you are deploying new nodes or deleting old. Then you get the crash map. That's why you got crash on Ceph. It's basically a list of OSDs, but from a different point of view. It's not only me. I'm always talking about different points of view. It's the very nature of Ceph. It tries to look at the problem from various kinds of perspective and then actually solve all the problems that arise. Crash solves the problem with failures. It strictly follows the failure domain hierarchy and puts the OSDs in different branches in this hierarchy. What does it mean? What is a failure domain? That's basically something that can fail. A disk can fail. So let's go up. A node can fail. Let's go up again. A whole rack of servers can fail. How far can we go? A row of racks, a server room, building, city, continent, planet, galaxy, universe. I don't think you will do such deployments, but it is possible. Without any problems, without any additional programming. It is there. And this is just the map. Then there's the algorithm that actually leverages this information in a very clever way. And the last map is the metadata servers map. This is actually rather new in the 10 series. It was added. Before that, you could have only one active metadata server. Now, the Ceph will handle behind the bars it for you. You can fire a few more in order to have some redundancy even here. But the thing is that for those applications that use the metadata, you need one entry point. And we will see later on why this is so. So we can at least have some active, passive sort of redundancy, speaking in terms of high available clusters. Actually, only one monitor and 2 OSDs are needed to deploy at least something which works better than just one hard drive. But basically what you get is a RAID 1, so why would you do that? But say for some purposes that might help, because RAID 1, you cannot scale that much. This, you can. So you might think of that. So if we look at the hierarchy of the disks, we just follow the failure domain hierarchy and see that the cluster consists of nodes, and those nodes contain OSDs, those nodes may contain monitors, those nodes may contain MDSs, and those nodes might be client. The thing here is that you want to distribute all of these things uniformly across the failure domain hierarchy. Say you got 2 server rooms. If one fails and all the monitors are there, who cares about your data in the other? It's not working. You have to think when you deploy it. That's basically what you do with any highly available cluster. So from those hands I saw earlier, I think you know what I'm talking about. Now, object placement. Finally, we got to the point where we can see what Ceph actually does with your data. As I mentioned, there are no files or directories, just object. What is an object? It can be any data, say number 1, number 10, or, for example, an ISO of some DVD or even bigger chunk of data. It doesn't matter. It's a binary blob and it's got some name. That's what you do. So it's sort of a key value store where the value can be really, really big. For these objects of various size, you want to find a balance across all OSDs with respect to various factors. First, capacity. You don't want to have some of your OSDs almost full and some of them unused. Why would you deploy them in the first place then? But also think of bandwidth. You want to have your data accessible rapidly, which means you have to provision it in that way. Also, you want to distribute this uniformly across all the nodes. If you have a node with 8 OSDs and 20 OSDs, you have to take this into account, and Ceph does. You can tackle with that, but usually leave the job to the default algorithm. It works surprisingly well. In order to distribute the objects across the storage, we use, as I said, the sets of OSDs, the placement groups. As I mentioned, it's any set of disks which can store an object. And basically, all you need to know is that you have a certain number of replicas. Therefore, you have a certain number of OSDs in a placement group. But imagine, from the example I gave earlier, you got 720 combinations, and you set up only, let's say, 300 placement groups, which is actually the default case. What does that mean? It means that for this number of disks, it's not actually useful to leverage the full scale, the full capabilities of those combinations, because it's just 10 disks. It's not that much scaling. But for 100 disks, it would make sense to actually pre-calculate more combinations, so you use more placement groups. Of course, you can reconfigure this during the cluster lifetime, and you can shrink it, you can grow it. It's rather simple. The thing here is that you've got a vast number of objects compared to the placement groups. So statistically speaking, if you do not do really stupid things, it will get distributed sort of uniformly. How do we do that? We use crush. It's controlled replication under scalable hashing. I always forget that term. What does this mean? This is a very clever algorithm that allows you to skip any central authority when deciding which placement groups to use. So, as I mentioned, the monitors govern the cluster, but you do not need to go through them when you actually store and retrieve the data. And that's because you're using crush, you got all the required metadata, let's say, and then you just use this algorithm to actually do some work. It means that each client computes what it has to contact and how. It also means that this is the place where you use the failure domain hierarchy in order to not only provide the uniform distribution, but also provide some means of keeping redundancy useful to you. As I mentioned, there's this failure domain hierarchy, which is basically a tree, just a data structure tree. And by properly configuring the failure domain hierarchy mapped onto this tree, you get a weighted tree. So when you are deciding where to put something, you just traverse this tree with this algorithm, and by applying the weights and other variables, you end up in a specific placement group. No matter when or who does this calculation in the cluster, you always arrive at the same placement group and use it for storing or retrieving the data. That's the crucial part. So yes, deterministic criteria, that's how we call it. And yes, we do not need any central authority. How we use this? Now I was talking only about sort of mathematical, theoretical stuff like algorithms and rather abstract stuff. But you need to implement this on wire. And that's where the RADOS comes in. It's a protocol, set of protocols which govern basically the crash execution. And it's not only for, say, file system metadata or the objects data, but all cluster metadata that needs to be distributed, and even for those advanced features which are built on top of the object storage itself. So there are separate layers in the RADOS set of protocols for that. For example, for RBD and, of course, Ceph file system metadata. In case you are wondering, it means reliable autonomic distribution object store set of protocols. So, then we come back to monitors, which should do the actual management in the failure domain hierarchy. As I said, it's basically a highly available cluster, nothing more, nothing less. So they do the voting, they reach the quorum, and when you are running a client, you just use one of them to connect to the cluster. And that's basically everything about them. If you include all the information about crash and RADOS, you now know everything about the Ceph architecture, and basically you should be able to write it from scratch after reading a few papers from 10 years ago and studying advanced C++ programming, but that's not a problem. So let's build some interesting applications on top of Ceph. That's what we use it for. For example, the Ceph file system. It's a Unix file system built on top of those objects in the storage. And it's got some advanced capabilities. It's got, of course, access control, ownership, and things like that, etc., etc. But there's one interesting thing. All the directory sizes are reported immediately. If you look at the directory, its size is the size of all objects it contains. There's no need to calculate anything. That's really handy if you are working with large data sets. Everything is pre-calculated, pre-stored there. Also, there are virtually no limits on file sizes. As long as you can keep adding OSDs, you can keep storing data in any single file, and you can have as much of them as you want in any directory. All you need is the running MDS, because the file system would be really, really slow without the metadata server. It's like you need to read some file and you would have to traverse all the metadata yourself. Here you just look it up in some hash table, which is handled by the metadata server. Also, interesting feature, you can have separate configurations of redundancy for the data and metadata. So yes, you can lose some file if anything fails and you do not have enough replicas of your data, but you'll keep it can keep your file system consistent if you got more replicas of the metadata, which are generally much smaller. That's achieved by using different pools for the data and metadata. So the metadata server basically uses this pool with metadata and provides immediately information about objects metadata. That's how you get this reasonable performance. And it is actually required for using Ceph file system. There's no implementation without running it. So if you would want to use it for something something other and also interesting, you could use it for providing a service like Amazon does. That's the S3 service, simple storage service. OpenStack, anyone? Swift, anyone? Hands? Nobody knows? Okay, you know OpenStack. That's basically a set of software which comprises a full cloud implementation, be it on premises or somewhere else. Swift is the component that can take Ceph as a backend and provides basically the same service as Amazon S3 does. And you can install it yourself on your hardware. Then what you use if you are running, for example, OpenStack, you use RADOS block devices for storing the data of your virtual machines, and you can actually boot them of those using, for example, KVM. It works surprisingly well. The thing is, they're built on top of those objects, and they're using many, many objects for each block device. And once again, it's another level of sort of attempt to distribute things uniformly. Not only the objects itself are distributed uniformly, but on top of that, if you create a block device, the objects of that block device will be, or there will be an attempt to distribute them uniformly across all available placement groups. That's really useful, not because of edit redundancy. Actually, it sort of counters the redundancy, but it improves the performance. It really improves the performance. And how do we do it? We use some naming conventions. Basically, all those objects have some names, and objects comprising a single RADOS block device have a prefix for their names, and then some naming scheme which is internally used by the librd library. And also, the library itself provides client-side caching. So if you are using a RADOS block device using the standard library, you can configure your caching on your client without any further configuration or further layers. It's built in. And it provides a true concurrent access, which can actually hit you in the foot. More on that later. So, on Ceph file system in a cloud environment, you would probably store some ISO images or configurations or basically any shared data. That's what you do. So, it's almost like there we've got a yeah, oh, one more slide. Ceph file system in user space. That's something new in Ceph revision 10. It's a bit slower than the in-kernel implementation, but it's more stable, and if it actually fails, it doesn't take down your whole system. And so that's really useful, and it's available as just normal fuse mount thing. So now it's like we got a guy who, for a bit of a change from his usual stunt of being sexist, racist, murderous, C-level executive, created a file system that can suit all our needs. Isn't that great? We've got in-kernel support since Linux 2633, which was released 6 years ago. That's the same for Ceph file system, and of course, RADOS block devices. If this would be a rock concert, I would probably shout something like, "Do you like Ceph?" And you would shout back, "Yeah, we do." Oh yeah, we might try that. "Do you like Ceph?" I'm not amused. Okay, the thing why I'm not amused is not only the lack of your reaction, but I know it's rather boring stuff, although I try to make it at least sort of interesting. But there are problems, and there are some huge problems. And actually, why I'm giving this talk is that we spent 10 months deploying Ceph in our company. And now it works, and we are really satisfied with that, but those are really painful 10 months. Not everything works as advertised, and you have to know that before you start. First, imagine you get a small cluster like 20 terabytes of data, yes, terabytes, and you mistype a number when creating a block device. You create a 20 petabyte device. Thin provisioning, cool, wow, rock and roll. Okay, then you have to wait for 8 days before you deprovision that, because Ceph magically tries to actually calculate for all those non-existing OSDs and everything that will be need to be allocated, and then tries to sort of release that. Then you wait, and then yes, profit. No, I don't think so. You have to think really carefully when using the thin provisioning. It can, as I said, hit you in the foot. But it must be said, everything worked flawlessly after that. It's just pain in the ass, but it works, so it didn't crash. Then again, RBD locking. All those nifty features of concurrent access really do work. But Linux kernel, well, you know, it's not exactly the best software in the world when it comes to multi-threading, locking, and things like that. So it's rather easy to come to a scenario when you access a single RBD from 2 machines, and it works as expected. Then you try to access the same RBD on 1 machine twice, and everything just crashes, and there's no way out except for rebooting the affected machine. Yes, everything ends up in D state, so you have to reboot. The same applies for Ceph file system in kernel implementation. So you are using all those files. By the way, this can happen even if you are just reading them. We actually encountered this situation in Ceph file system while accessing concurrently one ISO image, just reading it, nothing more. And one of the nodes just ended up in the waiting for IO completion state and never got out of it before we rebooted it. So it's terrible. Once again, no way to unmount the file system afterwards, and you have to reboot it. Then again, Ceph tries to be helpful. It fills your logs with various messages which are really useful and actually can help you with debugging certain problems apart from those logging problems I just mentioned. 100,000 lines of log files, nothing interesting there, yet the machine is unresponsive. Just happens. That's the main problems. How to solve them? Because it is actually possible to use it. You just have to think Ceph and not think Linux in this case. You have to think user space, because everything we got here can be used from user space. If you are using RBDs, what are you using them for? Usually for running some virtual machines. Okay, what are you using for running virtual machines these days? If you are running Linux, it'd probably be KVM or something similar. So why use Linux kernel and map the device on the node and then use it in the VM? Just plug it directly in the KVM using libRBD, and it is supported. You can use Ceph libRBD as a backend for storage devices in KVM. It works. It works perfectly well, and although people say that it's got some performance impact, we don't care. It works really fast enough, and if you're doing some real-time operations, you should not use Ceph. You should use something specifically tied to your needs. So that's it. What about the file system? Once again, as I mentioned, in version 10, you can mount it from user space using Fuse library, and once again, it works surprisingly well. If anything goes wrong, you can easily unmount it. But, and now is the strange part, nothing ever went wrong with this implementation. So there must be something wrong with the in-kernel implementation, which nobody actually wants to touch because it's sort of black box which somehow works, and that's how we keep it. So it is really stable, and it's got a decent performance. If you are fine with using Fuse in different scenarios, it will have the same performance in this scenario. I think one of the last problems we will have to tackle here is the performance of those block devices when being used as backends for virtual machines. If you are running a database workload on virtual machines which use Ceph as a backend, you're running into trouble. Because when you perform a database commit, the database system performs fsync, which gets propagated to the file system, which gets propagated to the KVM, and to Ceph itself. And Ceph itself completes I/O request, fsync, only after all the replicas have been written to actual OSDs. So it can be a really long time. What can you do? Well, you can use opportunistic caching and just forget about barriers and syncing. It will work, but then you have to provide another means of ensuring some reliability, which means using battery backups for your OSDs and things like that. Or you can give up running databases on top of that. That's all you can do right now. When I was actually reading the research paper about how the fsync is implemented, I thought that it might be an interesting, say, PhD project if someone would implement a caching mechanism that will ensure that at least one copy gets written, and then the fsync call will not wait for those remaining copies which are required for redundancy. So we get the data at least somewhere. I know it's not perfect, but I think it's worth studying and maybe doing some tests and measurements. So yes, that's what we do, and we always have to use backup battery. Now, the references. It looks like nobody got offended by the stripes I used there, okay. But anyway, we have to thank Ceph developers. We have to thank Yojin and Hedgehog for their hilarious comics. And we have to, if we want really to understand how this all works, read the paper. And I suggest you, if you're interested in deploying Ceph, even if you are not an academic person, read the paper referenced here. It's not long, it's like 20 pages, a few equations and few nice pictures. And you'll sort of get the notion of how it works underneath. And it's actually helpful even if you are deploying it afterwards. So that's it. Now, if you have any questions, we can answer them for you.
Have you tried Maxim? I think I can do it.
No. It has to be on record.
Have you tried the maximal file size of the Ceph file system? Because we were using version 0.9.4, and there were a limit for 1 terabyte for file size.
We haven't actually tried it, but some of those limits were raised substantially. I think that was in version 9?
Maybe in 9.
There's nothing new in this part of Ceph in version 10, but in 9 it was. And we started using Ceph with the 9 release, so that's... Okay. It should be there. We didn't try it.
Thank you, we'll try.
Anyone else? Oh, there's somebody.
Okay, one question about the fsync, because if I remember correctly, the Ceph have 2 configuration numbers. One is the number of replicas I want, and the second is the minimum number of replicas under which the Ceph will say, okay, I still take data, I still work. And I can say, okay, I want 4 replicas, and I can work under 2 replicas. So if the fsync wait for the full number or for the minimum number?
For the full number.
For the full number. So it will be maybe good about the PhD project. Somebody go and say, okay, we maybe flip some bits and say minimum number is fine, and put some configuration variable that says, okay, if somebody is so like cowboy looking and said, okay, for me minimum number is 1, and I'm happy with that. So that can be quite simple.
It might and it might not. I wouldn't judge, because the thing here is you have the minimum number of replicas where the cluster will actually work. So what we use it for is when we want to maintain, do some maintenance on some nodes, we just shut them down, and we've got configured a minimum number of replicas that it's okay. It just says the placement groups are in degraded states, but yeah, we'll continue to work with them and the clients will not notice. We see it in the health status and we have to deal with that, but that's what this configuration value is for. I think it might be really, from the user perspective, nice to use it actually even for this, because that's what the user wants. I have set up the minimum and I've set up the... It makes sense. It might be a nice research project. Anyone else? Okay, so if that's all, thank you for listening.